All right, chemistry guys, we are going through the gas laws guided practice. Now, we did this in class, but if we went too fast in class, or maybe you weren't here, or maybe you just want to hear the explanations again, then that's what this video is for. So, we're going through the gas laws guided practice. So, I'm going to show you, all the correct answers and what you need to be looking for when you're doing gas law problems. And yeah, so let's just jump right into it. So the first thing is, um, especially when you're using the ideal gas law, you want to be very aware of what unit of pressure you're using, because the R value that you end up using in the ideal gas law equation is pretty much dependent on the units of all the variables that are in that equation. But the really important one to focus on is the unit of pressure. So remember, your R values are, like 0.08206. I would use that R value if my pressure's in atmospheres. But I could also use 8.314 as my R value, but I would only use that if my pressure was in kilopascals, kPa. Or I think it's 62.36. That's another R value, but that's if your pressure was either millimeters of mercury or torr. And so we can make an R value for PSI, pounds per square inch, but you're never going to see that even if you take AP chemistry or something like that. So that's not a big deal. But we just want to get familiar with these different units and understand that these are all units of pressure. So I can convert from atmospheres to kPa or kPa to atmospheres. I can convert kPa to millimeters of mercury. I can convert kPa to PSI or vice versa. All these different units here are measurements of pressure. And I don't know why it got cut off on the document, but this should say 1.000 atmosphere. So 1 atmosphere, okay, is equal to 101.3 kilopascals, which is equal to 760 millimeters of mercury, which is the same value in torr. Really, torr and millimeters of mercury are the same unit, and that's equal to 14.7 psi, pounds per square inch. Now, you don't really need to know, pounds per square inch as a unit. It's never going to show up on a test or anything like that. But I'm putting it in here to give you kind of some perspective on, what 1 atmosphere is worth. So, like, if you know that your car tire pressure is probably between 30 and 40 psi, depending on what kind of car you drive and what kind of tires you have. So let's say around 35 psi. 1 atmosphere is worth about 15 psi. So the pressure in your car tire is more than double the pressure of the atmosphere. So just kind of giving you an idea of what the pressure of the atmosphere is, what's the pressure of the inside your car tire, that kind of thing. Okay, but let's go to the first part. So again, atmospheres, that's probably the unit of pressure we're going to stick with most of the time. When we get to the ideal gas law, we're probably going to be using 0.08206, so my pressure is going to be in atmospheres. Or if I'm using 0.08206 in the ideal gas law and I'm solving for P, pressure, then it's going to come out to be in atmospheres. So that's just something to think about. But how do we convert one unit of pressure to another unit of pressure? Well, we have the equalities, and it's just dimensional analysis. So let's look at number 1 here. We're converting 1.75 atmospheres to millimeters of mercury. So it's 760 millimeters of mercury for every 1 atmosphere. So if we take our 1.75 atmospheres and we multiply it by that ratio, and we got that ratio from the equality, 1.75 times 760, and I didn't write the answer here. I'm kind of annoyed by that, but it ends up being 1,330 millimeters of mercury. Okay. We can do the same thing here in number 2. We're going from kPa to torr, but notice here our ratio in number 1, it was something over 1. Usually our dimensional analysis ratios are something over 1 or 1 over something, but be careful. It's not going to be something over 1 or 1 over something here. It's going to be 760 torr over 101.3 kPa, because 101.3 kPa is equal to 760 torr. So we take our kPa, we multiply it by our ratio. So we multiply by 760, but we would divide by 101.3. So 509 times 760 divided by 101.3. And we get around 3,800, so 3,818. But if we round to 3 sig digs, we'll go 3,820, and that would be torr. Okay. All right. But again, and you don't have to have these equalities memorized. You just have to know how to do dimensional analysis with them if you have to convert from one pressure to another. So I think these are on the back of your periodic table formula sheet, so you should be good to go. All right. So now let's get into practice of the actual gas laws, the different equations you need to know. So the first type we're going to go through are what we call the proportional gas laws. That's going to be Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, and the combined gas law. So basically, these three, Boyle's, Charles', Gay-Lussac's, they all get combined into the combined gas law. So the combined gas law, remember, is just a combination of these three gas laws here. Avogadro's kind of stand alone, and we don't really use Avogadro that much. All Avogadro's law is saying is that amount of gas, moles of gas, is directly proportional to volume of gas if pressure and temperature are constant. So that should make sense. The more gas particles you have, the larger the volume they'll occupy. So as moles of gas increase, volume is going to increase if pressure and temperature are supposed to remain constant. Okay. So what I want us to, really make sure we understand is, have the combined gas law memorized. And, the way we're going to attack each question is, if we know it's a proportional gas law, which means you're given like an initial pressure and you're asked for the final pressure, or maybe you're given an initial temperature and a final temperature and you're asked to find, and you have an initial volume and you want to find the final volume. So it's always where, in these kinds of questions, you have to be given like two of each measurement, right? I got to be given two temperatures and one pressure, and I'm solving for the second pressure, right? So initial times initial equals final times final, or initial divided by initial equals final divided by final. Really, it's that kind of question. So if you know the combined gas law and you're looking at a question and then you're told that temperature stays constant. So like look at number one, it says assume there's no change in temperature. Well, if temperature is being held constant, cover up temperature, and then that's the gas law you use, okay? So if volume's held constant, get rid of V1 and V2, and now my gas law is P1 over T1 equals P2 over T2. If pressure's held constant, get rid of P1, get rid of P2, and now I'm doing V1 over T1 equals V2 over T2. So, and for gas laws, it's really not necessarily, you don't need them to know them by name, but you need to know what relationship they describe, okay? All right, so let's dive into this question. So it says, a contained gas has a pressure of 1.5 atmospheres and a volume of 6.5, okay, liters. What will the pressure be of the gas be if it's transferred to a 10-liter container? So we're changing volume from 6.5 to 10, okay? And we're told assume there is no change in temperature. Now, another thing that you can assume most of the time is that amount of gas, moles of gas, is staying constant. Notice there is no symbol for N in the combined gas law, okay? So usually when we're dealing with Boyle's law, Charles' law, Gay-Lussac's law, the other variable that's not a variable, the other thing that's staying constant is moles, amount of gas, number of gas particles, okay? So we find out what's being held constant, and it's temperature and amount. So that means if I take my combined gas law and I get rid of temperature, that's the equation I'm using. Now, you don't need to know that P1V1 equals P2V2. You don't need to know that that's called Boyle's law, but you can, it doesn't hurt. But what you do need to understand is this is showing an inverse relationship. So if pressure increases, volume decreases, or vice versa, right? And so that's why in part C here, when you're looking at a gas law problem, first figure out what equation you're going to use, and then you're just going to plug in your numbers and solve. But understand what to expect, because sometimes you might confuse, like what if you accidentally thought this was V1 and you paired this volume up with that pressure? No, that's P1 and that's V1. So this number and this number should be on this side of the equation, and this number should be on that side of the equation. So I always tell students to understand what to expect. We know it's an inverse relationship. And what happened to the volume? The volume went up. So we should expect the pressure to go down. So the pressure is currently 1.5. So if our answer is not less than 1.5, if our answer is greater than 1.5 atmospheres, we know we might have done something wrong. Or maybe we accidentally did P1 over V1 equals P2 over V2, which is a direct relationship. But pressure and volume have an inverse relationship. So again, if we ended up with a number here that was higher than the initial pressure, I know that's incorrect, because if volume goes up, I should understand that pressure should go down if we're talking about Boyle's law, all right? So we plug in our numbers. Notice I don't have the units written out. It's always a good idea to write your units. I just feel like it gets a little messy. But in any of these gas laws, if my initial pressure is atmospheres and I'm solving for P2, then that's going to be atmospheres. And you really don't have to worry about units when you're using these gas laws, except for the temperature unit. Remember, that has to be in Kelvin. But pressure could be kPa, and you could have kPa here, and then you're solving for kPa, or it could be millimeters of mercury, and you're solving for millimeters of mercury. And your volume doesn't have to be liters. It could be milliliters. You could plug in gallons, okay? It's just a direct relationship, okay? The only real unit you have to worry about when you're doing any of these gas laws is temperature. If you're plugging in a temperature value, it's got to be in Kelvin, okay? So we plug in our P1, our V1, here's our V2, we're solving for P2, so it'll be 1.65 times 6.5 divided by 10, and we get 0.975 atmospheres, okay? And, we double check, did pressure decrease? Yes, it did. That's what we were expecting, so we're probably right. Hopefully we did our math correctly, all right? Go to number 2, okay? It says a rigid container. Now, as soon as you see a rigid container, that means volume's being held constant, okay? So I don't have to have an equation that has volume in it, right? So if I go up to my combined gas law, I can get rid of volume, and it's probably going to be a Gay-Lussac's law, P1 over T1 equals P2 over T2, okay? The other thing that's being held constant in this question is moles of gas. So our temperature is at 50 degrees Celsius, and our pressure is 850 millimeters of mercury. And we want to know what P2 is going to be, what the new pressure is going to be if our temperature goes up to 100, okay? Now, watch out for this. If this were a multiple choice question, I bet choice A would be double this number, okay? Because what a lot of students are going to see is that the temperature doubled. And since pressure and temperature have a direct relationship, if the temperature doubles, the pressure should also double, okay? But remember, it's a direct relationship on the Kelvin scale, not the Celsius scale. So yes, the temperature is increasing, but on the Kelvin scale, if I converted this to Kelvin and this to Kelvin, it's not doubling on the Kelvin scale. So the pressure is going to go up because there is a direct relationship. So if temperature increases, the pressure is going to increase. But it's not going to double unless it's the Kelvin temperature that's doubling. Like if I go from 200 Kelvin to 400 Kelvin, yeah, my pressure would double. But that's not what's happening here. So watch out for that, especially if it's a multiple choice question. That's how, they always like to, you're rushing through, you forget to change it to Kelvin, you go, oh, the temperature doubled, so the pressure doubled, and choice A is 2 times this number, so I know I'm right, and I move on. So just, be careful with that, all right? Okay, so again, I know I'm using Gay-Lussac's law because we're getting rid of volume from the combined gas law, and the reason why we're getting rid of volume from the combined gas law is because it's being held constant. How do I know? It's in a rigid container, so it's not flexible, it's not like a balloon or anything, okay? And again, know what to expect. This is showing a direct relationship, so if temperature goes up, pressure should go up. And in our question, the temperature is increasing, so we should expect a pressure that's higher than 850 millimeters of mercury, okay? So we're going to go P1 over T1 equals P2 over T2. So my P1 is 850 millimeters of mercury, but notice that for T1, I wrote 323. Now, where did that come from? 50 degrees Celsius plus 273. that's the number in Kelvin. You have to convert, okay? And so notice that my T2 is 273 plus 100, so 373. So notice, yes, the Kelvin temperature is increasing, but that's not doubling. It's not doubling. So the pressure is not going to double, all right? So you got to be careful with that, all right? So, make sure we review how to do algebra, but it would be this times this divided by that, right? So this number times that number divided by that number, and that would give me P2, right? Cross multiply and then divide by 323, okay? So we get around 980 millimeters of mercury. So it did increase, okay, but it didn't double because the temperature did not double on the Kelvin scale, okay? All right, so let's move on to the next guy. All right, so again, here I have it blank. I'll scroll down for the answers. Okay, but we have a gas is in a flexible container that currently has a volume of 10 liters. So flexible container, that means the volume can change. Okay, so volume is a variable. The temperature of the gas is currently 25 degrees Celsius. What will the new volume be if the temperature is decreased to 0 degrees Celsius? Okay, so again, our temperature is in Celsius, so we're going to have to convert that to Kelvin when we use it in a gas law. But what's not changing? The pressure isn't changing. Okay, the flexible container is going to equalize with the pressure of the atmosphere. So if the pressure of the atmosphere is not changing, the balloon will shrink if the pressure inside decreases, but the balloon will increase if the pressure decreases, that kind of thing. But the pressure is not changing, and the amount of gas isn't changing. So if we go up to our combined gas law, we're getting rid of pressure. So we got V1 over T1 equals V2 over T2. Okay, so that's the gas law we're going to use. So another direct relationship. So here I'm scrolling down. So pressure and amount of gas are being held constant. So this is the gas law. If you want to know the name, it's Charles' law. Okay. Again, 10 liters was my V1 and 298. So 25 plus 273 was my T1. V2 is what I'm solving for. And 0 degrees Celsius is 273 Kelvin. Okay. And again, expect what the answer should be compared to the initial volume. So temperature is going down, so I expect volume to also decrease. So my answer should be less than 10 liters, okay? So again, solving for V2, we would do this number times 273 divided by 298, and we get 9.16 liters. So the volume did decrease, and so we should be feeling confident that we did everything right, okay? But notice I have my liters here, so remember this was 10 liters, so when I solve for V2, that's going to be in liters as well, okay? Here we go to number 4. All right, in this one, everything's being held constant, or everything's a variable except for moles. So the only thing being held constant is amount of gas. So this is when we're going to have to use the combined gas law. So we're doing P1 times V1 over T1 equals P2 times V2 over T2. Okay, and if you read the question here, we got 50 liters is our volume, and it's currently at 1.5 atmospheres, and we're at 275 Kelvin, okay? So this is V1, this is P1, and this is T1, okay? The gas is transferred to a 75-liter tank, so V2, okay? And now we have a new temperature of 500 Kelvin, so T2. And so what are we solving for? We're solving for P2. So we are given everything. So this is where, the combined gas law is pretty simple, it's not hard mathematically, but what's difficult is, interpreting the question, and you're going to be given 5 different measurements, and you have to solve for the 6th, right? So we have 5 numbers to plug in, and we have to solve for 1, okay? So we have 6 things here, we got to solve for one of them. So we're given 5 different numbers. And so it can kind of get confusing. It can be very easy to mistake this for T1, or, maybe call this V1, or this one's V2. Okay, so you gotta, make sure you're reading the question and know which numbers go where, okay? So I'm solving for P2. So if I take the combined gas law and I isolate P2, I get P2 is equal to P1 times V1 over T2, or times T2, divided by V2 times T1, okay? So P1 was 1.5 atmospheres, V1 was 50, but now we multiply by T2, which is 500. So the 500 goes up here, okay? Then we divide by V2, which was 75, and we divide by T1 as well, which was 275, okay? And since my P1 was in atmospheres, when I solve for P2, the units are going to be atmospheres, okay? Now, it's kind of hard with the combined gas law to know what to expect, okay? So the volume went up, right? So volume and pressure have an inverse relationship. So increasing the volume should bring the pressure down. But we also increase the temperature, and temperature and pressure have a direct relationship, okay? So we increase the volume, so the pressure should decrease a little bit from that. But since we increase the temperature, the pressure should increase from that. So really, what's going to be our new pressure? Is it going to be greater than the initial pressure, or is it going to be less than the initial pressure? Is it going to be equal to the initial pressure? Well, it depends on, how much did we change the volume versus how much did we change the temperature, right? So, we went from 50 to 75, but we went from 275 to 500. So it looks like the temperature increased more than the volume increased. So I think overall the pressure should be a little bit higher than what it was originally, because the direct relationship was a bigger change than the inverse relationship. But again, we know it's going to be maybe different than this value, but it's kind of hard to know what to expect. So if you plug in everything correctly, you end up with 1.8 atmospheres. So it's a little bit higher than the initial pressure. But remember, we did one change that should cause the pressure to go down, and then we did another change that causes the pressure to go up. So which one wins? Well, it's which one did we change the most, okay? All right, and then number 5, it's just saying, I don't have a practice problem with Avogadro's law. It's just saying if the only thing that's being held, or if the variables are volume and moles, and so the things being held constant are pressure and temperature, then that's when you would use Avogadro's law. And it really doesn't matter. You can do N1 over V1 equals N2 over V2, or you could do V1 over N1 equals V2 over N2. What you understand is volume and amount of gas, volume and moles of gas have a direct relationship. And if you need to know the name, that's Avogadro's law, okay? All right, so those were the proportional gas laws. Now we're moving on to gas laws where we're not given an initial volume and we're asked for the final volume, or we're not given an initial temperature and asked for the final temperature, okay? These are other equations we can use based on what we know about gases. And the first one is Dalton's law of partial pressure, okay? So I think I have it written down. Do I have it? Let's go back up to the blank page. Maybe, sorry. Right here. So the first Dalton laws of partial pressure is very easy. It says the total pressure inside a mixture of gases equals the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C, okay? And then, you could have gas D, gas E, gas F, all right? You have any number of gases in a mixture. And then the other kind of Dalton's law of partial pressure says the partial pressure of a gas, so the partial pressure of gas A, is equal to what we call the mole fraction of gas A times the total pressure, okay? So we're going to use both of these in the next couple of examples, all right? So the first one, pretty easy. We have gas A at 10 atmospheres. We have gas B at 5 atmospheres. We're told the total pressure is 16 atmospheres, and we want to know what's the partial pressure of gas C. So we have 3 gases, gas A, gas B, gas C. The sum of their partial pressures should equal their total pressure. Well, we know that the total pressure is 16. We know that gas A is 10 and gas B is 5. So what's left over? Gas C, 1 atmosphere, okay? Now, this is one, especially be careful. Number 2, it's asking which of these gases has the greatest partial pressure. And a lot of students want to go with 100 grams of oxygen because you have a higher mass of oxygen. But remember, it's not about mass. It's about the number of particles. So it's about how many moles you have. So you got to, if you're given grams of gas and you want to know which one has the higher partial pressure, which one has the lower partial pressure, you really need to figure out which one do you have more moles of, and that's going to have the highest partial pressure, which one you have less moles of, that's going to have the lowest partial pressure. And you got to remember, oxygen is diatomic. So 100 divided by 32, 20 divided by 2, or 2.02. 50 divided by 28, or 28.02, right? You got to convert this to moles. A lot of students are going to just jump on oxygen and say that has the greatest partial pressure because that's the bigger number. But again, it's not about grams, it's about moles. So we have 3.125 moles of oxygen, we have 9.9 moles of hydrogen, and we only have 1.78 moles of nitrogen. So the answer is hydrogen. Hydrogen would have the higher partial pressure because we have the most of particles of it in the mixture. Then oxygen would be the second most, and nitrogen would have the lowest partial pressure. Okay, so hydrogen has the greatest partial pressure here. Okay, so here in part A of number 2, we're trying to figure out what the partial pressure of nitrogen is, and we're given the total pressure of the mixture. So it's the same mixture that's described up here. Now we have the total pressure. So what do we do to find the partial pressure of nitrogen? We'll have to figure out the mole fraction of nitrogen and multiply it by the total pressure. Now mole fraction is really easy. It's just moles of part divided by total moles. So the mole fraction of nitrogen would be moles of nitrogen divided by the total moles of gas in the system. So remember, we just figured out how many moles of nitrogen we have, so we plug that in at top. And then we do this plus this plus this. So moles of oxygen plus moles of hydrogen plus moles of nitrogen would be total moles. So 1.78 divided by 14.805, that would be the mole fraction of nitrogen. And then we'd multiply that by the total pressure, which was 1,000 kPa. So it comes out to be 120.2 kPa. And be careful, because I almost made the mistake when making the key. I forgot. It asked for atmospheres. So how do we go from kPa to atmospheres? We divide by 101.3. If we go back to our equalities. So 1 atmosphere is equal to 101.3 kPa. So if we have kPa, if we divide by 101.3, that'll give us atmospheres. So in terms of kPa, the partial pressure of nitrogen in this mixture is 120.2, and in terms of atmospheres, it's 1.2 or 1.19 atmospheres. Okay. All right. Now, question number 3 for Dalton's law. This is one where, whenever you know you're calculating the pressure above water, okay, the pressure above water. Meaning you're collecting a gas over water. You have to understand that some of the water will vaporize, and the gas that you're collecting is not just that gas, it's gas plus some water vapor. So the total pressure inside the container where you're collecting this gas that's being produced over water is going to be, the total pressure is going to be the pressure of the gas you're collecting plus the pressure of water at that temperature. And the pressure of water at that temperature is going to be called the vapor pressure of water at that temperature. And so to answer this question, you will always be given the vapor pressure of water at that particular temperature, okay? So when you're reading a question, you're like, what's going on here? And they say, oh, by the way, the vapor pressure of water is this. It's just a simple Dalton's law question. So let me just show you it worked out, okay? So the total pressure equals the partial pressure of the gas we're collecting, I'm just calling it gas A, plus the vapor pressure of water at that temperature. Well, they gave us the total pressure, 3.95, and they gave us the pressure of water at that temperature, 0.12. So all we have to do is 3.95 minus 0.12, and we get the pressure of the gas, okay? So very simple, very straightforward, but you just kind of have to understand what's going on, right? So a gas is being produced in this aqueous solution. It's bubbling out, right, evolving out of the solution, but we're collecting it over water. But at the same time that gas is bubbling out, we're also going to get some water vaporizing, okay? The higher the temperature, the more water we're going to get vaporizing as well, and the higher this vapor pressure would be. So different temperatures of water have different vapor pressures. But it's not something you would have to memorize. It would be something you're given within the question, and you just got to know what to do with it. All right. Okay. So the next gas law we're going to be talking about is Graham's law, and it says the rate of, and it could be the rate of effusion or the rate of diffusion. It doesn't matter. But how fast gas 1 is effusing divided by how fast gas 2 is effusing is equal to the square root of the molar mass of gas 2 over the square root of the molar mass of gas 1. So if I put, whatever rate I put here for gas, like if I put gas A's rate here, then the molar mass of gas A goes here, right? If I put gas B on top over here, then the molar mass of gas B goes over here, okay? So these capital M's in Graham's law don't stand for molarity, they stand for molar mass, okay? So in this question, we're told that an SO2 balloon has a rate of effusion of 2 milliliters per minute. So the SO2 is escaping at a rate of 2 milliliters per minute, okay? And we're told an unknown gas in a different balloon, but at the same temperature, is effusing twice as fast. So if SO2's rate is 2, then the other gas rate would be double that, 4. Okay, so I'm going to say 2 over 4 equals the square root of our unknown gas molar mass divided by the square root of 64. So 64 is just the molar mass of SO2, right? Sulfur is around 32 and O2 is 32, so 64. And a lot of times in Graham's law questions, SO2 is used because you can just say its molar mass is 64 and you know what the square root of 64 is without a calculator, okay? So when we solve for x comes out to be 16. So our unknown gas has a molar mass of 16 grams per mole. Okay, so that's what we figured out here. Okay, if you had to identify the gas, they might give you a list of gases, and you would just figure out which one has a molar mass of 16. Probably methane. Methane's what, 16.05 grams per mole. So I'm guessing our unknown gas is CH4. Okay, but again, that would, they would have to give you some choices, and you would just pick the gas that has the closest mass to this number, okay? All right, so now the ideal gas law, all right? So Pivner, PV equals nRT. This is where we gotta be careful with all of our units, okay? And the R value I'm gonna use all the time is 0.08206. So what does that mean? If I'm using this R value, my pressures in atmospheres, my volume has to be liters, so if it was milliliters, I'd have to convert it. My amount of gas, N, is always moles. R, again, I get to pick what R value I want, and I always use this one, so that. And then temperature, just like all the other gas laws, has to be Kelvin, okay? But in this gas law, right, Boyle's law, volume could be milliliters. Charles' law, volume could be milliliters. But in the ideal gas law, volume has to be liters, okay, every time, no matter what R value you decide to use, okay? We're given the volume, we're given the pressure, and we're given the temperature. We want to solve for the moles of gas that we have, in this case, air. So PV equals nRT, so N equals PV over RT. So we plug in our pressure. Now, where did I get 2.58? Well, I was given 37.9 PSI. I can't use PSI if I'm using this R value. So I would divide this by 14.7. Right? Go back to our pressure equalities at the top of the worksheet. So 37.9 divided by 14.7, that's where the 2.58 came from, all right? So that's how many atmospheres of pressure I have. My volume was in liters, so I can keep it there. My R value is 0.08206. And remember, it's 303, not 30. I have to do 30 plus 273 to plug in my temperature. So when I solve, I get 3.63 moles of air. Okay, so I have that many moles of air, okay? Then the next question is asking how many molecules of oxygen are in that same tire. Well, the first thing we got to remember is air is not just oxygen, right? Air is mostly nitrogen, oxygen, other gases, okay? So to answer this question, you'd have to know a little bit more about our atmosphere and what percent of our atmosphere is oxygen. So our percentage of oxygen in the atmosphere is around 21%. It's not something you have to memorize. It would be given to you. If I asked you this question on a test, I'd have to tell you that it's 21%. So if we take 0.21% and we multiply it by the total moles we have, that will give us just moles of oxygen. So if I take 0.21 times the answer we got up here, 3.63, I get moles of oxygen. And then once I have moles of oxygen, multiply by Avogadro's number to figure out how many molecules of oxygen. If I took 3.63 and I multiplied it by Avogadro's number, that would give me how many total particles I have. And the majority of those particles would be nitrogen molecules, right? But this is how we would figure out just the oxygen in our car tire, okay? All right, number two, we're given a big tank, 150-liter tank. It has 300 grams of helium gas in it, and the temperature is being held at 298 Kelvin, and we want to know the pressure. So again, how do I know to use this instead of, like Boyle's law or something? Well, notice I'm just given one value of each thing, right? If this is one of those proportional gas laws like Charles' law, I might be given an initial volume, but I have to be given a final volume, right? If I'm only given one volume and one amount of gas and one temperature of the gas, then it's probably the ideal gas law, right? So we're solving for P. So PV equals nRT, so P equals nRT over V, okay? So I can plug in, so N is moles. So I have 300 grams, so how did I get 75? 300 divided by 4. Right? The molar mass of helium is 4. So 300 divided by 4 is how many moles of helium I have. I'm going to use 0.08206. 298 is my Kelvin value, and my volume is in liters, so I can plug that right in. And when I solve for P, I get 12.2. And how do I know it's atmospheres? Well, if you're solving for P in the ideal gas law and you're using this R value, the unit is atmosphere every time. Okay, so 12.2 atmospheres is the pressure inside this tank. Okay. All right, and then in number 3, what mass of nitrogen gas can be found in a 25-liter tank at STP? So, a lot of you should just do it the easy way and say, okay, 25 divided by 22.4, and then times the molar mass of nitrogen. So if I do 25 divided by 22.4 times 28.02, I get this number. But you can always use the ideal gas law. So remember, STP is a temperature measurement and it's a pressure measurement, okay? So I have the volume, I have the temperature, and I have the pressure. So I can use Pivnert to solve for moles, all right? So the pressure, what's standard pressure? One atmosphere. So that's where that came from, okay? My volume is 25, so I got 1 times 25 here, okay? I'll use 0.08206 because I put 1 atmosphere. If I wanted to, I could put 760 millimeters of mercury here, but then I would have to use a different R value, 62.36. If I wanted to, I could put 101.3 kPa because that's 1 atmosphere. 1 atmosphere is 101.3 kPa, so I could plug that in, but then I'd have to use 8.314 as my R value. Okay, but if I want to use this as my R value, then the pressure I'm going to plug in is atmospheres. So standard pressure is 1. And then where did the 273 Kelvin from? Well, that's standard temperature. Standard temperature is 0 degrees Celsius, which is 273 Kelvin. Okay, and then so I solve for moles and then multiply by the molar mass of nitrogen. I got to remember that it's diatomic, so not 14.01, but 28.02, and I get 31.3. Okay, but I would have gotten the same number if I saw STP and I go, oh yeah, I can say 1 mole of any gas takes up 22.4 liters of space. I could, if I did 25 divided by 22.4 and then multiplied by the molar mass of nitrogen, I would get the same answer. But this is just kind of a lesson. You can always use the ideal gas law, but you have to remember that STP is a temperature value and a pressure value that you can use to plug into the ideal gas law. All right? All right, so that's the video. I think it might be too long to post in Schoology, so I'll post a link to YouTube. I hope you have a wonderful day, and I hope you are liking the gas laws. Take it easy.